today I wanted to show you how to start with the Input Devices week. So if we go to fabacademy.org website, and then we go to content 2021 schedule and input devices. So there are all kinds of sensors that you can explore. So probably the sensor that you should choose should be related to your final project. So we were discussing earlier an accelerometer. Then we were talking about the GPS sensor just now. Then I think Solomon is building a CNC machine, and for him, it would be useful to explore a Hall effect sensor, so which is able to sense a magnetic field, temperature sensors, light sensors. For light sensors, we were discussing with Kittia that it would be interesting to use this no, not light sensor. It was more. So we were discussing that you could use the accelerometer, either 3-axis or 6-axis. So because, and then for Ranjit, it would be nice to explore one of the microphones. So I actually tried to make a little board that would try to communicate with the digital MEMS microphone with I2S library. So this I2S protocol, as I learned yesterday, it's a tricky one. So I'm not sure whether it's gonna be successful, but we went halfway last year using the analog version of this MEMS microphone, but then we have a variety of electret microphones, and we could easily use actually those. Then step response, so Russian wanted to play around with those, with that, and it could be useful for Dinan as well. Yeah, so image is another thing, but I think Russian already managed to do something with the ESP cam and use the camera input as a sensor, so that's also a possibility. So that's a possibility, but I would rather support to localize this assignment and really make sense out of it. I would rather focus on one of the sensors that you can actually attach to a board. So it's also a possibility for you to practice the PCB design and production one more time, so you get more comfortable with the machines and the process. So you should design a board, and you should attach a sensor, and you should write code that actually reads that sensor. And in order to get started, so you pick your sensor. So you pick a sensor, and then you also identify its where it's located, where you can find more information about it. So it's usually the data sheet. So and I usually just go to the Fab inventory, so the dreaded spreadsheet, and look up the sensor that I'm looking for. Hall effect, yeah. So I'm gonna play around with this Hall effect sensor. And then I go to DigiKey. And here I can find more information about it. So I'm gonna switch to English language. We are interested in the data sheet. So you click this here, open it up. And usually the first page of it gives a good impression what it is, what you can do with it. So you can see so we are gonna have these SOT23 packaged sensors, and then you can read the description and functional. So this is what's going on inside of the sensor, and what is relevant is what each of the pins mean. So see, it needs input power, pin 1 VCC, and ground, and then the V out is the output signal. So which basically shows it provides you with some voltage. So supply voltage should be 5 volts approximately. But in the design, I'm actually going to assume that that this is 3 volts, just to show you, to remind you to double check the typical supply voltage, because it could be also lower. It could be 3.3 volts. And you should use some sort of a voltage divider in order to cut down the voltage. So magnetic characteristics, all these kind of things. And usually in the data sheets, you can also find a typical application diagram. I wonder if it's going to be also like this. Yeah, so typical application circuit. So what we can read from this is that, yeah, there's a power supply here, the positive connection and a negative connection, and then there's a bypass capacitor that should be put as close as possible to the to the chip. So it's 0.1 microfarad, and then the V out is the voltage out, which goes to the microcontroller, to an analog pin of a microcontroller, in our case an ATtiny chip. And here so we have these footprints already in the Fab library, but in case you find the sensor which doesn't have footprints, then usually in the data sheets you can find the numbers, so the sizing of those. And or if you have inspiration, you could also check whether that specific component has a 3D model, and use one of the 3D modeling packages and model these parts to contribute to the library. This is for the through-hole component part. Yeah, and with this, it should be enough to actually start up. Oh, well, another thing is that where you can start out is by going to the actual site, Fab Academy site of the Input Devices page, and check one of the Neil's Hello World designs. It's a Hall effect sensor over here, components, and see how it's done here. And here, this looks like this. This is the actual sensor in the corner of the board. This is the ISP connector. So this is for the older chips. This is ATtiny 85, I think, or 45. Let's see. Yeah, 45. ATtiny 45. And yeah, this is the, instead of UPDI programming connector, it was still using the AVR. And also you see that it doesn't use the recommended bypass capacitor next to the sensor. So this is something that we could fix. But yeah, the board looks pretty much like this. And there's even a test code included. So that, but it's only in C. Probably you might want to, and here's with 412. So probably you might want to write it in Arduino code. Yeah, so here's our UPDI version. So just next to the UPDI, there's the sensor. It's also quite far from one of the bypass capacitors. So this is a good bypass capacitor for the chip, but there's no bypass capacitor for the actual magnetic sensor. And then here, there's an Arduino code file. So here, what is happening is that we are reading multiple readings. So sampling it 100 times and then averaging it. So just really low level, but you could do a better job on top of this. So, okay, so once, so now we have explored what is there. So we can go to KiCad and create a new project. And I'm going to go to desktop and demos. make a new folder and call this whole effect. And I'm going to start out with the schematic. And we're adding the parts that we need. I'm going to start out with 80 tiny 412. And the sensor. And you can find it by using the search bar like this. And for both of these, we will need 2 bypass capacitors. So one is going to be this, and then I'm going to copy this by hitting C. And I'm going to add a value. So it's going to be 1 microfarad, and for this one, it was 0.1. I'm hovering this and hitting V in order to access the value field. Then we'll need a few connectors. So we need Fab FTDI connector. It's going to be here, and then we need the Fab UPDI connector. And in Carl's context, you might be using some sort of header. And I started adding the mail, so the through-hole mail headers in the library. And those you can find by typing the TH, by targeting the TH part of the library. So I'm kind of trying to come up with the best naming scheme for the header specifically. So that's like a separate library project on its own. I'm going to put a bit more energy into this, but at the moment I have added so these 4, so 5-pin, 6-pin, 7 and 8-pin through-hole connectors. There should be, I think it's just going to make everything from 2 to 16, but you can select one of those, and they have already associated footprints for the through-hole for the headers. But it's, yeah, separate. So basically, you should let's discuss this separately when you're working, when you're bored. I'm just gonna, I want to, maybe there would be also a motivation for me to iterate on the library in terms of these headers, and we could fix this together. I'm just going to leave this here. And on top of that, so what do we need else? So we have the bypass, this one, that one. I usually tend also to add power LED. So I'm just going to add a LED somewhere next to the power. And I'm going to add a resistor. Is this from the Fab? Yeah. And so for some of you, it's going to be probably needed. So if you really need to double check what is the voltage or the power rating for the sensor. And some of the sensors, they are powered with 3.3 volts. And for that, you will need to convert the incoming 5 volts to 3.3. So you need a linear voltage regulator. And so here we have some in the Fab library. So it's like the 3.1 that is going to convert the incoming voltage to 3.3 volts if it doesn't exceed 100 milliamps. So this is good for, you know, just reading a sensor. So this should be enough. But for example, if you want to power something more like a Wi-Fi module, so something that needs more current, then you might go with like a 1 ampere one. But this is converting any incoming voltage. Let's say if you're powering, if you want to reuse the voltage that you are using for your motor driver, and you want to use that in order to power also the microcontroller. So then if the incoming voltage is, let's say 24, volts, then this chip is going to convert it to 5 volts. But in this case, we're going to take this one. It's just 100 milliamps is just enough for our purpose. And let's try to stitch it together somehow. I'm going to start with the header over here. So ground and VCC, these are, I'm going to actually flip it around. So, and so I already see which ones I'm not going to connect. I'm not going to need the RTS, and I'm not going to need the CTS. And I'm going to add a label to the RX and TX. Like so, then separate those and add the power flags over here. So 5 volts are going to be here. And then ground is going to be here. And I also need the power flags. So since it's the incoming voltage, incoming power here. So with these done, what is going on here? Let's move this aside a little bit, and oh no, just gonna connect this to 5 volts. I'm just gonna copy this symbol and hovering it and hitting C, and I'm putting it here. And what I need to do here is add a ground symbol, also hovering the ground symbol, hitting C to copy it. And then for the regulator, so this is the input voltage, and I just need to connect it to 5 volts. I'm gonna copy this, rotate it, put it here, and I'm gonna copy this, connect this to ground, like so. And as for the output voltage, I'm gonna draw a wire and add a label that's gonna be 3.3 volts. Actually, instead of using this, I could use one of the power symbols over here. 3.3 volts. So, all right. And then as for these bypass capacitors, I want to connect them. I want to place them. I want to remember to place them as close as possible to the chips that they are protecting. So here, I want to connect to, so let's say this Hall effect sensor is going to be using 3 volts. I'm going to copy this 3 volts and put them here. This is not the real scenario. I'm just showing this. Just if in case your board uses, your sensor uses 3.3 volts. If one of the microphones is using 3.3 volts, the accelerometer is using 3.3. You connect this to ground, and then we need the output. And for the output, I'm going to label this as whole. So here, so the UPDI connector. Okay, let's deal with this also. Like so. And here, then we can also connect all the necessary connections. So also just recently, so if you're using the I2C protocol, not or I2C protocol, then you can easily tell which pins you have to use for connecting those. So these are extracted from the MegaTinyCore library, so that you don't have to look up the library, so the image there, so you can use these labels to do the mappings a bit more easily. And then also added here the DAC or digital to analog converter label. So if you want to connect this, use this pin for playing back audio, so to convert bytes into actual voltage levels, then you can use this pin. And MegaTinyCore is gonna know which of the pins of this chip is actually configured to do so. And so this will be able to go straight into an amplifier. And what do we need now? We need to connect these TX and RX pins to our serial connection, to the FTDI connection that we have. And remember that we have to flip those. So for TX, it's going to be RX. And for RX, it's going to be TX. So this corresponds to the labels that they added over here. And then for the PA1, this is that we're going to use to measure the sensor. So I'm going to add a whole label over here. And then we basically have 2 pins left in order to break out. And I'm going to do so. I'm going to name this VK1 as and VK2. And here for the header, so since I haven't added like a real 2-pin header, I'm gonna make these as non-connects and connect them to VK1 and VK2. Like so. Then I'm going to annotate and debug. So there's not, something is not right. Ah, yeah, so that's driven. So we haven't connected this to any voltage yet. So just gonna connect this to, and actually it is that, so the ATtiny1 series, you can power up with either 5 or 3 volts. So actually you could just, you could also use power it up with 3.3 volts. Like that. So in case you're using multiple sensors that you're using 3.3 volts and you don't want to use 2 separate voltages on your board, then you can just power it with 3.3, no problem. No errors. And then as for the mappings, we can check. But all of the Fab library parts, they already have footprint mappings. Yeah, here we go. So you see all the symbols are actually mapped to specific footprints. Here we have those. Then for the through-hole one, we have this. So these through-hole headers are designed with a thing in mind that you need to drill 1.5 millimeter holes in order to be able to insert the 1.5 millimeter rivets into them. I actually have a few unedited videos that have to be edited this week, which show how to use a different software other than mods in order to do this in a much easier way. So I will notify you once that is done. And then we can move on to the PCB part. Over here, insert the netlist, and start laying it out. I'm not gonna, yeah, one thing that I wanted to maybe introduce you with in this video, yeah, of course, it was the through-hole headers, but it was also vias. So for some sensors, it's gonna be quite hard to find the kind of route the connections around the components. So yeah, I'm gonna move this a little bit further just to show how to solve that by using vias and say moving your PCB manufacturing skills into the level where you can actually deal with double-sided boards. So here I'm placing, so this is the actual voltage divider. So this is the part which is going to convert the incoming 5 volts from the FTDI connector, which is going to convert it to 3.3 volts. And then, so we're going to use that to power up our microcontroller also. And before it enters the microcontroller, we're going to use this 1 microfarad bypass capacitor over here. And then as for the sensor, just going to check which is the, so I'm going to try to put it as close as possible to the pin, which is going to read that sensor. And it also needs a bypass capacitor, which is this. And we're going to try to put it as close as possible to the sensor over here. And the rest of it is the UPDI connector, which I think I'm just going to put it on the other side somewhere here. And then the breakout pins, I'm going to try to put somewhere might be sometimes that you know, there are some parts that are overlapping. So let's say that you, so let's also take care of the predefined sizes that we want the clearance to be 0.4 millimeters and the track width to be also 0.4 millimeters. And so I told you that I want to talk about vias. So vias are interconnections in between layers. So you drill holes and you insert copper rings into these holes so that you can connect the front side of the board with the other side of the board. This board that I made yesterday in order to test the sensor, it's a double-sided one. So you see there are traces on the front side, and then there are like little holes that are actually connecting these traces to some of the traces on the other side over here. In order to make these in KiCad, you need to understand the concept of vias. And it starts with defining the via size. So the drill that we're going to use for the smaller vias is going to be 0.8. And the via size should be bigger than the drill because it needs like a little ring, copper ring around the hole to be able to connect to the actual copper layer of that layer. I usually make it 2 times bigger. So if the hole is 0.8, then 1.6 millimeters should be enough copper. Okay, and how this works is that, let's say we have a ground connection over here. And now we want this 5-volt line to cross over somehow. We don't want to, let's say we don't want to go around, but we want to jump over this one. And the way it is done is that you start drawing the trace over here, and then you hit V on a keyboard, which stands for via. And then you click 1 more time in order to place it. And KiCad moves to the other layer in order to draw the trace here. And then once you are satisfied with the location, you can hit another V and place a via, and you're back to the main layer. So now you have a 2-layer connection. So instead of using a 0-ohm resistor, you can go to the other side of the board and you can add a connection. You can jump over a connection over there. And yeah, so, and here also, instead of, let's say, going around, I could just place a via and then go to the connection over here. And yeah, it seems that here's a real use case where you could use it. To jump over. So here, via, put it here, jump over to somewhere here. Actually, I can connect to this one over here, because the way we are planning to work with these headers is that we're going to drill holes, each of those 1.5 millimeters in diameter, and insert bigger rivets. So the smaller rivets, so the smaller vias will be done with 0.8 millimeter vias. Here, if you take a look at this board, you can see here in the middle there are like smaller holes. So these are the 0.8 millimeter vias. So on the bottom part, there are the bigger ones. So these are the 1.5 millimeter vias. And at the lab, and also in a separate video, I'm going to show you how to work with these, how to insert them. So basically, you insert them from one side, and then you use a set of tools in order to anchor them and yeah, finish them from the other side. So you have different drills for those. So we have 1.5 millimeter drills and 0.8 millimeter drills. So for these specific things to be done. I mean, normally you would maybe not use so many vias, but we just wanted to demonstrate to you how this works. So usually you would try to avoid the vias as much as possible. So keep it as much as, because single-sided is much easier to mill as double-sided. But in this case, okay, let's just go wild with all the vias. And I'm gonna draw a simple outline for this one using the 1 millimeter grid. So grids are really useful. So yeah, if you want to get a really precise outline, and I can be sometimes very picky so that I don't have floating points after the dimensions, XY dimensions of the board. So I would use the 1 millimeter grid, and make sure that you're on the edge cuts, of course. Here I want to be on the edge. And so also what I wanted to show with this one was that so this design can be used, so will be used with milling with a copper cam. So not mods, but copper cam. So instead of milling this, you can export Gerber files. And we can avoid doing some additional things in the design here that we did for mods. For example, we did draw a margin around, and we also made an additional user drawings folder in order to make the SVG files so that they would be compatible with mods. So if you plan to work with CopperCam, then that's not needed. And then on top of that, I'm gonna also do a copper fill, copper pour, and with the double-sided, what you can do a copper fill on the other side of the board. So you can use the bottom side of the board as the ground layer. So this is what I usually do. So let's actually do that. No, this is more add filled zones. So I think I need to go to a layer where this can be done. Yeah, and here I can select the layer where I want it to be. I want it to be on the bottom layer. And I'm just gonna make it as a ground fill. And we need a via that actually connects to the ground layer from all the ground elements over here. So I'm gonna start with one here. So I'm gonna start drawing and a via, then and hit B. No, B to redraw. So now it filled it up because it actually felt the connection with these ones. And then instead of doing an underground or bottom layer trace to the underground element over here, so we see that these are connected. So the way how we're gonna connect them together is that I'm just gonna add a via here to the ground, to the bottom layer, and hit B in order to redraw it. So now it's connected. So now there's no rat's nest. Now we need also to connect these two together somehow. So now I can also add a via from here, for example. Like so, and now it seems that it's fine. We can run the DRC design rule check. So this is all right. And now in order to export it, instead of using the file export, we're going to use the plot tool. And here, so this is useful when you're sending your boards to, let's say, a manufacturing service like a new PCBWay or Seed Studio or Euro PCB. So one of these, and kind of a step or like an intermediate step is milling PCBs with a copper cam that we have at the lab. And manufacturing houses usually need information about all the layers that you want to have because they also have more capabilities. So they need not only the front copper and bottom copper, but they need the paste layers for the solder paste to be applied. They need the silk layers for the labels to be printed on the board. They need the mask layers for the solder mask to be applied. And of course, yeah, the edge cuts. In our case, we're not going to need all these because we don't have the capabilities necessarily, or it's sort of tricky to use them at this point. And then we don't need the footprint values. We don't need the footprint references. And also we don't want to exclude the PCB edge layer from other layers. You'll understand why when we're going to cover copper cam. And then excluding pads from silk screen, so that's also not relevant really. And what we want to do, we want to generate a Gerber job file and use the extended format, include netlist attributes. This is also optional. I don't think that we need all these, but I'm just going to leave them on for now. And then we need to specify the output directory. And I usually call it Gerbers. Hit open and yes, and then I hit plot. It's going to generate the Gerber files. And then another thing that we need to do is generate drill files. So you click on this. So the drill format is usually specified as Epsilon. Now, so if you dig deeper into the PCB manufacturing process, the manufacturing houses, they usually have drilling machines, which are also produced by the same brand. Epsilon, so Epsilon drills, so to drill holes into PCBs. And we need to check this PTH and NPTH in single file. Yeah, so in our case, we just need to merge them in single file because we don't want too much trouble with the drill files. Yeah, I wish I could explain more about those. Then this is okay. We need to select the suppress leading zeros option here. That's important. Then drill units are going to be millimeters, drill origin absolute, but take care of the origin in copper cam afterwards. And then you generate drill file. generated it in the Gerber's directory of the project. And you close it. And another, so when you go back to the project view, so the KiCad project viewer, then you will see this Gerber viewer icon over here. So which is another tool in the KiCad tool family, which allows you to examine your Gerber files. And we can open up plot files, so which are all the Gerber. And here you can just double check whether all the layers are correct. So you can enable, disable them. So this is the front copper. Then here we have the edge cuts separately, and this is the back copper. You just check whether they overlap nicely. Yeah. And then I think we can also open the drill files here. Now I'm wondering where those were added. Yeah, so these are the drills. Then we have the front copper layer on top of it, edge cuts, and the bottom layer. Yeah, and I wonder, do we have the 3D viewer? No, let's go to the 3D viewer here. Yeah, so there are just some LEDs that are missing, and also the sensor. But this is how we are expecting our board to look like. Yeah, I think this is enough for today. So I'm going to try to edit also the additional videos which cover the milling part. But otherwise, if you manage to produce the design with your with a sensor you chose earlier, then just try to catch me, and I'm going to show you individually how to work with the machine.